So just a quick about us. I'm Mike Kershaw. I did the Kismet wireless sniffer. I did some Zigbee sniffing stuff. I'm part of some other projects making sniffing hardware. So if it involves sniffing anything in the airwaves, I'm probably poking at it at some degree.
Hi, I'm Mike Ryan. Day job, I'm an InfoSec security consultant, but I have to state my disclaimer. I'm here speaking only for myself, not as a representative of my employer, and I'm just lucky to be here today. And I do Bluetooth low energy research, which is also wireless. And yeah.
Right, so our main motivations for this. Wireshark's a great tool with decoders for a ton of different protocols, but there's a lot of things out there that don't generate network interfaces. So how do we get those to come into the Wireshark fold where, watching people make really crappy homebrew decoders is infuriating. So how do we get it so that people can easily bring whatever random project they're working on and feed it directly into Wireshark in a user-friendly, easily managed way?
And before we go on, has anybody in here been to ShmooCon before? Anyone? Couple people? So these little shark guys here, in the great tradition of the ShmooCon Shmooballs, if you have a problem with anything we're saying or you think we're not doing a good job, let us know. Let us know just like that. We welcome the assault.
Although try to avoid hitting the laptop.
We don't have any liquids on the table, you're good. Don't worry, we won't fight back.
Much. So the requirements at looking at how to extend Wireshark for this would be developer simplicity. Wireshark's a big, kind of scary code base because it does a ton of awesome, kind of scary stuff. So having people that are just trying to get, a little bit of code from a USB device dumped into Wireshark, telling them, oh, you need to understand, 100,000 lines of code and do all this stuff, we probably won't get any real uptake on it. And we don't want to break anything that Wireshark does already. We don't want to ruin its cross-platform work. We don't want to make weird custom things that only work sometimes. We need to make it really easy for end users to handle modifying things, because the whole point of pulling it into Wireshark and making it easier to use is making it so that you don't have to remember 14 weird little combinations for some program to dump to a PCAP to then go open into Wireshark and figure out what's going on. And we don't want to compromise any of the security. So Wireshark does a good job of privilege separation. We need to make sure we keep that intact and don't provide new ways to create security problems with Wireshark.
So today in Wireshark, as I'm sure you all know, you can capture from network devices and load captures from PCAP files, but it's all pretty network-centric. Wireshark was born of an Ethernet sniffer. Everything that's kind of grown on since then has been an extension of that. Now it is already able to handle some non-Ethernet traffic today. You've got Wi-Fi with radio tab headers, token ring, USB, and some other things. But everything that you want to sniff with Wireshark, pretty much to a first approximation, has to be a network interface or a file. So if you're not using a network interface and you still want to take advantage of Wireshark's dissectors and other neat features, you've got a couple options. You can log it to a file and open it in Wireshark. That's a pain because then you have to remember how to run multiple tools. You have to be able to run the command line capture tool and remember all the weird little single character options for that. And then you can't look at the capture in real time. There's some tricks for using a TUN-tap device and stuffing packets into a virtual network device. I don't even know how to do this. He put that bullet point on there, so it's complicated. In
Linux, because of some stuff I was doing with Kismet back in like 2.6.1 or whatever, I made it so you can change the DLT, so you can actually make a TUN-tap Wi-Fi interface or a TUN-tap Zigbee interface or something, but only in Linux. You can't do it in OS X, you can't do it in Windows, so that's not a great option.
And so your last option is to write to a pipe, like a named pipe or a FIFO. And it's pretty good. There's a lot of support for this already, but it's not exactly turnkey. You have to, there's a manual process involved setting up Wireshark to look for the pipe, load from the pipe, and you still usually have to launch the capture device manually. So, not awesome.
So where do we need to get to? Well, we need to not break capture devices. we need to not force compiling plugins directly into Wireshark, because then that would mean, you know, every distribution or every person building Wireshark on their own is going to have to get the whole build environment set up, get the development stuff. On Windows, they'll have to get all that stuff set up. We don't want to deal with that.
Not to mention that if you want to get anything included with the core Wireshark, you have to go through the whole process of getting accepted into the core, which is non-trivial, and a couple of versions behind most major distributions too.
And yeah, we want to make it really easy. People doing, you know, random custom projects versus people we really want to support aren't going to really spend a lot of time on this because it's not their primary focus. So, you know, part of the problem now is, you know, your focus is Bluetooth capture. You really don't want to be a GUI expert. You don't want to be a Wireshark expert. You don't want to figure out how to compile on Windows. You just want your project to work and maybe to see some packets. And we want to present a standard Wireshark UI. If it's completely unintelligible what comes out of this thing, then it's really not going to be any use to anybody. So the main problems we have for implementing capturing from things that aren't network devices. Wireshark and PCAP really like network interfaces. They're designed around them. All the main network interfaces are more or less configured the same way. You know, it's all Ethernet look-alike, other than a few outliers, and they all have the same config windows. They all act the same. Running random binaries as part of Wireshark is really terrifying from a security standpoint. And things that don't act like network devices are going to need weird custom configs.
So the solution is that, as we mentioned, Wireshark and PCAP can read from pipes. So pipes are great because they're multi-platform and they're already pretty well supported. So we really just need to extend that functionality a bit. So that pipes give us the way to actually get the data into Wireshark. We still have to do things like create the GUI. So what we've done is we create a simple configuration grammar that lets you define custom UI elements, things like a checkbox or maybe a frequency selection dialog box. And that all comes out of this configuration grammar that's purely text-based, so any typical developer should be able to handle it. We also have the Extcap binary itself handle privilege separation. Wireshark typically is run as a low rights user. PCAP is a little bit fuzzy, but Wireshark itself is low rights. So we want to launch we want the binaries themselves. If you need to have a set UID root to access a certain feature or something, have the Extcap binary itself handle that. But Wireshark shouldn't have to worry about it, neither should PCAP. And finally, we're really just trying to have as small of a footprint as possible inside Wireshark itself.
Yeah, I think the entire diff that includes all the documentation, all the parsers, the GTK generation stuff, and the modifications to Wireshark comes in at under 3,000 lines. So it's a pretty small change set. So the way we architected it is, you know, each plugin, we call them plugins, but they don't get loaded as a shared object or anything. They're an executable. So who's ever making the capture tool makes an executable that provides this functionality. They know what they need. They know what privileges they need. We don't care. We don't care what language it's in because it's not integrated into the code. It's not a shared object being loaded. So it can be in, you know, it can be a C binary. It can be Windows exe. It could be a Perl script or a Bash script. Whatever. Anything that can handle some arguments. So we give it a basic set of arguments that it really has to respond to. It has to be able to take a FIFO. It has to accept an argument to list what interfaces it supports. It has to accept an argument for what DLTs they have. And it has to accept an argument that says start actually doing something and write it to this FIFO. It writes a PCAP file using standard libpcap. You know, you just open the pipe as if it was a file, and then you can just dump to it as if, you know, with all your standard code, almost no changes. So if you can log to a file, you can integrate with this already. And the config grammar is meant to be really simple. As we mentioned for the security, the Extcaps are launched by the Wireshark binary itself, so it's running as a low privilege user. There's no more; they get no more privileges to begin with than whatever you started Wireshark as. Whatever people write is what they get. I mean, you can provide UDEV rules for your devices. You can, you know, tell them to install a suid root, whatever needs to happen. But Wireshark doesn't care. The config grammar itself, it's non-Turing. It's not a language. It's not anything more than some basic markup. So the entirety of the parsing is really look for the beginning and brace, look for the end brace, look for an equal sign. There's no escaping, there's no nested stuff, there's no real way to hide anything in there.
There's no XML entity expansion vulns.
Yeah, it's not interpreted in any way. It's just the minimal amount needed to break up arguments into something you can automatically handle.
Okay, so I'll talk about the grammar a little bit. It's really basic. Everything is made up of elements that look like the first line. You've got a required type, and then you have any number of attribute value pairs. At least one, but as many as you want. Each type we call a sentence, and that's it. It's really simple to generate. You can generate this from printf or print or whatever your
Echo.
language has. Echo. We have a proof of concept that's written as a shell script, and it's simple to parse. There's no evaluation, no escaping, no turring. It's literally just pattern matching. So interface sentences are a first example of this. One of the things that a capture binary has to be able to do is enumerate the interfaces that it supports. So for example, an Ubertooth capture might have, if you've got multiple Ubertooth devices plugged into the system, you'll have multiple Ubertooth lines.
Uberteeth?
Uberteeth.
Ubertooths?
The unofficial, official plural of Ubertooth is Uberteeth, just for the record. So those two interface lines down below are examples of that. You see interface declares the sentence, and then you've got a display name that Wireshark will display called interface1, and a value that's sort of an equivalent to like eth0 or wlan0 called int1 or int2. And we intend for those to sort of be unique to each Extcap. So the Ubertooth one would have Ubertooth0, Ubertooth1, so on and so forth.
Also on those, the external capture binary can put whatever they need to in there. So if you can extract a serial number from the device, you can use that to identify them uniquely. If you can't get a serial number, but you can get like the path in the USB system, you can use that as the identifier. It doesn't matter what it is. It's not really meant to be user visible. It's just, this is how you find it later, and then displays what gets shown to the user. So, and then multiple interfaces can be supported by the same binary. It just provides multiple interface statements. We keep independent configs for each interface, so you can have all your settings for interface 1 and then a whole different set of settings for interface 2. So if you have 2 Uberteeth plugged in, one can be on one channel, one can be on another, or whatever like that. And since you provide the list of interfaces, whatever you need to do to find the interfaces, it could be a static list of serial ports that you look at to see if it's one of your devices. It could be scanning the USB bus. It could even be something onto the remote network, just talking out over TCP, finding a broadcast, and going, okay, I have these interfaces, expose them to Wireshark. So then we need to be able to tell Wireshark what DLTs, what data link types we have. So is this an Ethernet? Is it a Bluetooth file or a capture? Is it Zigbee or whatever it is? Normally PCAP would do that by querying the interface and seeing what DLTs it supports. Since we can't do that here, the program will return any number of DLT sentences for the interfaces it supports. So you still need to get a DLT assigned for whatever your project is, but after that you can do whatever you need.
And the libpcap guys have gotten to a backlog of DLTs. So if you apply for one now, you might actually get one. Yeah, I can do this one. So arguments are the most complex thing that we have to handle, mainly because you can have multiple values for each argument, multiple types of arguments. So we support several types currently: int is integer, double, text fields, booleans, checkbox lists, and they can be populated GTK types like selectors or radio buttons. So you could have like a frequency selector or maybe a list of things. And we even support tooltips, so you can highlight things and give the user some little helpful text for making their choice. So this is where we start to get a little bit deeper into the guts. Every argument has a call equals argument. That's what literally gets passed to the command line of the Extcap binary. So you can have like -- long arg, like -- frequency, or -a, or something like that. The type itself determines how Wireshark displays it. That would be like your selector or your checkbox or your text fields. And some of them are already also populated with value sentences. So if your device only supports like a couple of channels, you could say value like a channel 1, channel 2, so on and so forth. So here are a couple examples. This first one is argument number 0. It gets called frequency is what gets passed on the command line, and the display is frequency. It's an integer, and here you see that we actually have range support, so you don't have to list out all 80 channels. You can just say, oh, channel 2400 to 2480. We've got a default and a tooltip value. And the second one is a Boolean, which is a, is that displayed as a checkbox? Yeah. And that would be like, do you want hopping or not?
So then there's value sentences. So you can have multiple value sentences associated with an argument. So that's how you populate, things that are one call that take multiple static inputs. So like a group of radio boxes would have a value sentence for each radio button. A selector, like the interface selection list, would have values for each line in the selector. Checkbox lists, which would look like the interface selection list, but with a checkbox so you can pick each category in there, would all look like selectors. And it's just the number of the argument it refers to, the value that gets passed to the argument call, and the display value that shows up. So it's really simple to plug in that way. So when it gets called, when you're finally done configuring things, we just take each arg sentence, take the data from the UI, build a list of whatever calls were in it, and tell it, here's all your calls, execute, point at this FIFO. That's the entirety of what your capture program would need to handle to interface with this. So we wanted to make it as hard as possible for the user to screw up, because they like to screw things up. Since we're talking random weird hardware, where we're getting random weird arguments. For example, we're looking at a lot of software radio stuff, where they use scientific notation heavily, because you're talking about 100 megahertz. Well, you can either type out 100, 000, 000. Did I put 6 zeros or 7? Hang on, go back and count. No. Or you just do 100E6. Done. So we implemented that. It's just little things that try to make it simpler. Range checking will be able to happen in the UI. It's one of the things we need to finish up doing. But so we'll actually be able to tell the user, this is out of range for what the program said it handles. Fix it.
So the actual requirements as an Extcap author. Your Extcap must respond to a handful of arguments that we have documented. It must be able to write to a PCAP stream to a named pipe, which is provided on the command line. It must flush the pipe after each packet to keep the UI responsive. That's it. It's really, really, really easy because we want people to actually use this. Question?
Do you actually need to flush the pipe after each packet, or can it be flushed in the middle of packet?
So the question is, does it need to be flushed after each packet, or can it be flushed in the middle? I think it can be flushed in the middle, and Wireshark might buffer it. I don't know.
Actually, USB pickup flushes. It's not really determined where USB pickup flashes. But it just reads some block of data and flashes it.
Yeah, he was saying so the USB PCAP code he's working on will read a block of data and then flush it, and it's not entirely deterministic. The reason we need the flushing after you open the file and we say after each packet, just because if you write a bunch of PCAP data to a named pipe and then don't flush it, then it's in your binaries, or it's in the external binaries buffers. And when the kernel gets around to it, it'll flush it, and then it'll appear in the named pipe. Then Wireshark will see it. Then it'll do something. As long as you're flushing that pipe regularly, so that there's a continual stream of packets coming into Wireshark, then the UI will show them more or less real time. So it shouldn't.
No, yeah, well, I don't interrupt. It's within Wireshark or within Dubcap actually, we, as our fellow, read a PCAP record header, and then try to read that many bytes, and we'll just block until we get that many bytes.
Yeah, Jared was just confirming that dumpcap will block until it gets the appropriate number of bytes for the packet. So yeah, you just need to be able to flush it regularly is really the key item, because otherwise it will never get into the pipe from your program's buffers, and it'll just be sitting there waiting.
You'll get like 10 packets at a time. Question in the back.
So what about remote captures? Can you use them like netcat type systems?
What about remote captures? Can you use them like netcap?
Netcat.
Netcat.
Yeah.
Has that already been done to death, and this would be open for
So there already is remote capture support in Wireshark, like RPCap. I don't see why you couldn't just run dump some PCAP into Netcat and pipe that into Wireshark as well. It's totally reasonable. I've done something similar to that over SSH with Wireshark's built-in pipe support in order to do capture on a remote system. So, pretty close.
Yeah, you could actually absolutely make a little shell script that that executes SSH with a host key or a pub key or whatever, and then dump it straight in. Yeah.
Okay. So Wireshark pipes. So it turns out Wireshark has had pipe support for a really long time. When I was preparing to do, thank you, Gerald. When I was preparing to do this work, I was kind of worried about how much work it was going to be to support pipes, and then I was like, oh hey, actually I don't have to worry at all. So, and we really didn't change very much at all. We really more or less slapped a nicer GUI on it. There's a little bit more involved, like getting DLTs from the devices and actually execing the Extcaps when it comes time to capture, but it's pretty much, the title of this talk should be how we wrapped pipes in a GUI. So in case you haven't seen it before, there's your typical capture options dialog. If you hit that manage interfaces button, you'll get the foreground window, and you can just click new and give a path to a pipe on your system. You can call make FIFO with that. So that's really all we wrapped. We just wrapped around that in a nicer, gave it a fresh coat of paint, more or less. But this still is here in case you want to do it the old-fashioned manual way anyway. So this is the old way that, or the quote-unquote traditional way that Wireshark actually goes through a full capture. You launch Wireshark, it calls out to dump PCAP to get a list of all the interfaces. Then when you go to start capturing from an interface, you get a list of all the DLTs. Some interfaces have support for multiple link layer types. Then you select your options on how to capture from a GUI. That GUI is fixed and cooked into the code. Then you pass the arguments for capturing into dump PCAP. So everything in this slide boils down to calls to libpcap, which means that Wireshark, dump PCAP, and libpcap all need to be taught anytime you want to have new interfaces. And if you look at the code now, you'll see that's how, mine is blanking, the 802.11 stuff. Radio tap.
Yep.
That's how radio tap is built in. At every place in the code where these options get called, there's a new branch of code for radio tap.
Or air PCAP.
Air PCAP. And if you wanted to add something new up until before Extcap, you would have to do the same thing. The new and improved way is, remember we said we don't want to break anything that's existing in Wireshark. So we still leave all the old code in place. We just add some new branches. So after we call dump PCAP to get all the PCAP interfaces, we iterate over all the Extcaps and ask them for a list of their interfaces. When we open up the capture options dialog, we still call dump PCAP-L to get the DLTs from the PCAPs, but we also iterate over all the Extcaps and list the DLTs for each interface that they gave us. The static GUI remains, but we call Extcap with --config. That generates the grammar. Wireshark internally parses that grammar and builds a GUI based on those options. You select your checkboxes, all that stuff. Finally, we still call dump PCAP, but if you're capturing from an Extcap, first we launch the Extcap itself with all the options as specified, with the addition of a FIFO that gets created, and Extcap will block on writes to that FIFO. Then we still launch dump PCAP, but instead of launching it with the name of a network interface, we launch it with the name of a pipe. So the actual flow of data into Wireshark is exactly the same as before. It's just that there's an extra binary that gets called to stuff data into a pipe rather than directly originating from dump PCAP. And this is the part you've all been waiting for, the demo.
So here's Wireshark running, and here's the list of interfaces per usual. And you'll notice at the top we've got, 2 additional ones. So those are both generated by those. So we can do and you can see that we're just generating the same grammar there. We can do and that's dumping, the config grammar we talked about before. So if we go back here and we double click on it, there's the modified capture window. So everything from the capture filter up is the static stuff that's always been in Wireshark, and everything from here down is the stuff we've dynamically added in. So you've got the booleans, you've got the checkbox lists, and whatnot. And we've also got the Ubertooth 1 grammar, so it lets you configure the Bluetooth low energy support. And you can even do multi-device capture.
So those are Bluetooth low energy packets. And
so we've got Bluetooth low energy.
that's being generated by this, captured by the Ubertooth 1 there.
And then we have Zigbee 802.15.4 data transmitted by one board here and captured by another one over there. So the Ubertooth is using libUSB talking over USB bus for that, and the Kisbee is using CDC ACM serial.
And these are both being captured in real time. There's no smoke and mirrors here, into the same PCAP NG file.
So the demo worked. So in case it failed, we had some screenshots prepared.
Oh no, that didn't work.
Except one of them didn't function. Great. But you just saw this for real. So some things we need to still work on with this is we need some better error handling. Right now we don't capture, so we don't catch violations of the range and whatnot. We don't catch if you told it was an int and gave it a float or a something like that. We don't really catch that. We need to kill off open processes better. Right now, if the capture doesn't detect a SIG pipe when Wireshark stops capturing, it's just going to keep running in the background, but it's relatively minor. It's a little thing. And we haven't done any testing on Windows yet, but it's just enumerating a directory, running executables, and writing to pipes. So we're not anticipating any problems, but we haven't tested. So then we were coming up with this, things we've already converted to Extcap, started converting to Extcap, or which we think would be able to use Extcap to good advantage.
Okay, so can I have the Ubertooth? So first piece of hardware, Ubertooth 1. This is an open source Bluetooth, open source software, open source hardware Bluetooth sniffing platform designed by Mike Osman. He was here last year with Mike and gave a talk on something else. And so Bluetooth sniffing is pretty hard. You can't just plug a Bluetooth dongle in and sniff it the same way you can with 802.11. So you actually have to build your own custom hardware and do all sorts of work to do that. So this device here allows for capture at the baseband of Bluetooth and Bluetooth low energy. So the top picture is this device here, the Ubertooth 1. The bottom picture is the Ubertooth 0. I believe 8 exists. Don't worry about that guy. So the Ubertooth, from the system's perspective, when it's operating in classic Bluetooth mode, it just sends a stream of radio data to the operating system. It just sends bits, like zeros and ones. And then libUSB translates those into something that your software can interface with. And then on the PC, you start looking for the beginning of Bluetooth frames and that sort of thing. This code is able to generate PCAPs, but it can't emulate a device yet. We're still working on it. Now, the Ubertooth 1 Bluetooth low energy mode is quite a bit richer. Bluetooth low energy goes by many names. It's called Bluetooth low energy, BTLE, Bluetooth Smart, or sometimes incorrectly Bluetooth 4.0. It's way simpler than classic Bluetooth. We can actually sniff it pretty effectively. And I've got some injection code in the works. So it's used in some interesting places. On the left, we've got a heart monitor. On the right, we've got a wireless door lock. And there's used in a lot of sports equipment. I also have to say, I'm not picking on these vendors. These are just examples. So the Extcap itself, you just saw demonstrated here. That's about 100 lines of Python. More than half of that is just dealing with the get-opt flags, and then most of the rest is generating the config grammar. It's really, really, really lightweight wrapper around an existing command line tool that generated PCAP files, but was unable to display them in any kind of GUI. This is pretty much a perfect example of what we want to support. Just slap a GUI on something and get real-time capture from it.
So the second piece of hardware we were just demoing is a thing I made last year called the Kisby, which is similarly open source hardware, open source software. It's meant to let you capture 802.15.4, which is the underlying protocol beneath Zigbee, and a number of others, 6LoWPAN and some other things. So it exports either over a CDC ACM emulated serial device on USB, or there's a little Bluetooth adapter on it, so it's a serial port Bluetooth for connecting to phones and Android and whatnot, so you can sniff that way. So it's definitely not a network device, and there's not really any sane way to make it act like a network device. Linux definitely doesn't believe this thing is an 802.15.4 adapter. I don't think Linux even really understands 802.15.4 as a network adapter. So it's just a little board. It's got a radio module and Bluetooth and USB. So the existing code for Kisby was it's a relatively simple script where it just uses Pi serial to interface to the USB serial port. It already has writing to PCAP files, although I had to use Scapy to do it because I couldn't find a decent libpcap library for Python. The whole thing was about 350 lines of Python before we started. Threw in some arg parser code into the Python, did some validation on the serial interfaces so that we could try to scan ones that were currently plugged in and active, so we could figure out what ones to present to the UI. We had to accept -- FIFO instead of -- file. Added a couple flush calls. That was it. It was 100 lines of code different to support making a GUI in Wireshark. And again, similar to the Ubertooth code, most of that was just printing out the grammar stuff. It's not complicated, but if you're still printing out 20 lines, that's 20 lines changed. The other project that we think is going to benefit from this is a project that Mike Osman is running as part of the DARPA Cyber Fast Track initiative, where it's multiple PHY layer capture devices, primarily wired, using a USB 3 FPGA board. So it'll be one big FPGA on USB 3 and then multiple boards that plug into that. As far as we know, it's going to be the first open source USB 3 stack. They're all networky devices, but they're not presented as network interfaces because we're doing a custom tap on them. So it'll be passed through tapping on gigabit Ethernet, USB 3, HDMI, RS-232, and there's some talk about trying to make a very fast software-defined radio module that plugs into it. So yeah, it's just an example of some of the things that are involved in that project. That's the main FPGA board, which Jared Boone designed.
Open source.
It is open source. You're welcome to go and try and make that and solder it. It's also 8-layer. That's the first prototype of the GigE board that I was involved in designing. So it captures multiple PHY layer through different interfaces. There's already some USB decoders in Wireshark. There's, of course, the Ethernet decoders are already done. I have no idea how we might present HDMI to Wireshark at the moment or why, but this will let us plug USB 3 dumper code straight into Wireshark with pipes. So instead of generating a 2 or 8 or 10 gig PCAP file and trying to load it, we'll be able to at least look at it somewhat live. And also, software-defined radio is becoming big lately. So an SDR is basically an antenna and a digitizer and a whole lot of processing behind it. All the DSP is done on the host computer. Instead of having a little dedicated radio here, you have a much larger system, but which can handle any protocol within its tuning frequency. So if you can see it, you can decode it in theory if you write the code to do it, which is the problem right now. It's really expensive in terms of the amount of power it needs and the amount of computing power it needs, but it's super, super flexible. So a lot of people are going to be using it to discover new things that are going on, or to help develop new protocols, or to investigate what's already out there. It used to be really expensive and rare. Recently, in the past 6 to 8 months, it's become almost a commodity. It's kind of ridiculous. The software now for SDR work is still mostly coming from the educational academic forum, where it's someone did this decoding for their thesis and don't necessarily care about the code anymore. But now that the hardware is something that everybody can get, we're hoping the software is going to catch up really soon. So some of the hardware that's out now for capturing random things over the air. The Hack RF, again by Mike Osman. We love Mike Osman. He does awesome things.
Mike's the guy.
He's making a low-cost, really flexible software-defined radio. It would have been difficult to make it work like a network interface, but now we don't have to. The Hack RF is going to be 30 megahertz to 6 gigahertz, which is insane, and 20 megahertz bandwidth. So you can actually capture a full 11G Wi-Fi channel and do software decode, or create your own Wi-Fi packets from the PLCP layer up if you wanted, because it can also transmit.
You can do evil things. Also, we have one of these if you want to come see it and you're all excited about SDR.
We'll have it up on the table. So that's what the Hack RF looks like. That's Mudge's dog, who was the head of the DARPA Cyber Fast Track initiative until his term concluded this spring. The next one is the Realtek RTL DVB tuner. It's meant to capture digital TV in Europe. Someone discovered you can get it to return raw radio IQ data. So it's 60 megahertz to 2.2 gigahertz. There's some significant gaps here and there due to the tuners, but that's still really amazing. It's a piece of crap. It's $20, but it's $20. You can, for $20, you can pick up airplane position beacons, pager networks, which of course you wouldn't do in the U.S. You can pick up FM radio. You can look at weather satellites. You can look at like people were detecting the CubeSats, the Nexus 1s that people put in orbit recently. You could pick up with this for $20. Buy one for each thing you want to do. So you can get them on Amazon. Also coming soon is the Blade RF, which was a Kickstarter project this spring, and they actually should be shipping next week or the week after. They're capturing 300 megahertz to 3.8 gigahertz at 40 megahertz, and they're dumping over USB 3. So you can actually, in theory, capture 11N on 2.4 gigahertz and get both channels with this thing. I haven't seen it yet, but $400. It's not $20, but it's not $2,000 either. So there's one of their Blade RFs, in this case, hooked up to a Raspberry Pi. I don't know what they're doing hooking it up to a Raspberry Pi because it's not going to have the processing power.
It has an FPGA.
It does.
So they do all the processing on the board.
So Thomas is saying the Blade RF does have an FPGA on it, so you can offload a lot of the processing to there. Yeah, probably, but
You have a few options. You can get the cheap one, which is $400, or the more expensive one, which is 600 or 650. You have a bigger FPGA on it.
there's one that's 400, there's one that's 650. The big one has a bigger FPGA.
But the Hack RF is better. Go Mike Osman.
So right now, almost all the SDR stuff on Linux anyway goes through GNU Radio, which is open source SDR radio software. It's architected as multiple blocks, so they can be written in C or I've seen them written in really weird things. But ultimately there's a Python interface to almost all of them. But I've seen the underlying stuff written in really weird things. So it's designed as multiple pluggable blocks. It's trivial, kinda, to chain decoder blocks and then get them to export to a PCAP file. If it's a PCAP file, we can turn that into a pipe, which means we can take the GNU radio output, dump it into, wrap it with some Extcap, and dump it into Wireshark directly. We've actually already been contacted by a student in France, I believe, who's working on a Google Summer Code sponsored project to do 802.11 decode with a software radio, and he wanted to interface that with Wireshark, so he'll be able to dump that. He'll be using this to dump that right in. So just some things you can decode already. ADSB and ACARS, Wi-Fi, Zigbee, you can do with the software-defined radio. You can do satellite communications. You can look at POC, SAG, and Flex. You can look at APRS, all sorts of stuff. If it talks wireless in packets, it's probably a target for doing something neat with software-defined radio now. So that'll all be pluggable in, or plug-inable now. Neither of those are words. So we're hoping now that this hardware is really cheap, we're going to be seeing a lot more people looking at these more interesting protocols that until now we needed $2,000 to mess with. So just to recap it all.
So we defined a simple grammar so you can build UIs without having to worry about GTK details. We defined an interface so you can write tools really easily. And we're working on like cleaning it up and getting it ready to actually go into the core. We have a repo you can check out if you want to play with it, but ultimately, this is going to go into Wireshark, right, Gerald? Sure. Okay. And basically, the bottom line: anything that isn't a kernel netif can go through Extcap and take advantage of all the benefits of Wireshark. So, with that, are there any questions?
Configuration grammar. I can understand why you didn't want to do XML. You have my sympathy for that. But why did you invent a new one? Didn't you go with JSON or YAML or something like that?
So the question is, first, yes, XML is horrible, and I appreciate you not shoving that down our throats. Why did we invent our own and not use another grammar that already existed like JSON or YAML? So I can answer why we didn't use JSON, because it's actually Turing complete. Or at least it'll reference itself, which makes it so both JSON and YAML can reference themselves. So we definitely don't want to do that. I don't know. You wrote the grammar.
Yeah, basically we didn't want to use anything like Lua that was an actual scripting language. We didn't really want to use getting an ECMA parse. You can kind of parse JSON without being an ECMA parser, but it's a big pain. And ultimately, we just didn't need anything that complex. I looked at JSON briefly, but for what we needed, it seemed easier and smaller to do that. And we didn't want to bring in any more libraries that Wireshark wasn't already using.
I'm just I'm an API guy, right? So, I look at it from the user's point of view, the developer who's actually using your product, and that strikes me as that you can go with something that's very, very easy. Let's just say it.
So we also didn't want to try to integrate any of those parsers into the code. The parser that we have now is only a couple hundred lines, so there's that too.
Also, part of it is we're expecting the developer is going to be generating this with printf, so they're not going to include an ECMA generation. They're not going to have a block of data that they're going to need to feed to a JSON presenter to serialize or anything like that. So, 6 of one, half dozen of the other. We kind of figured that there's only like 6 types, and everything's a value pair. So.
Other questions? Comments? Gerald?
One of the first things, assuming they add this to Wireshark, one of the first things that 1,000 people are going to try to do is write up a config to connect to Secure Shell running on their box elsewhere. How are you going to handle that?
So the question is, how are we going to handle people who really want to, the first thing that people are going to do when they get this is try to write a script to connect to SSH to capture on a remote box. What are we going to do about this?
Specifically, passwords.
How
would you handle that?
How would you handle passwords? We should probably just write an interface for SSH and make it not work with passwords. Set up host keys, or pub key based auth rather.
I mean, the alternate answer, which I'm just doing off the cuff, is we could just define a password variable type, but I don't like that because it's going to put the password on the command line. So, no. But
well, I think you are hinting at a deeper question, which is what about arguments that you don't want showing up in the output of a PS? It would not be really hard to dump those into a file that you pass as an argument and just require the Extcap to be smart about it. As the Extcap parser, or as the Extcap author, it's kind of your responsibility for that. But there does have to be support in the Wireshark side code for that. So first bug opened by Gerald himself. Anything else? Going once. Well, thank you very much. This was Mike and Mike.